We're going to be having a talk on diffieqgpu.jl with Oscar Smith. So I will hand it off to you.
So yeah, as previously mentioned, I'm Oscar. I work for JuliaHub. Pretty much all of the work in this talk was done by Uktarsh, who's at Julia Lab MIT CSAIL. But due to some travel issues, he's not able to be here today, and so I'm presenting this. First of all, why do we want GPUs? First of all, actually, why aren't my slides switching properly? Okay, so this is your differential equation, or ordinary differential equation, initial value problem. So you have f of upt equals du dt, and you have a time interval, and you have an initial condition. And we want to solve these, and we like to solve things in parallel where we can, but unfortunately for an initial value problem, it's a fundamentally fairly serial task, because to know the time at t, you need to know the time at t minus delta t first, and so you can't parallelize that easily. However, there's lots of situations in which you want to solve a bunch of problems. So you want to say, if I vary my parameters a little bit for process variation, how will it look like if I'm solving 10,000 differential equations that are all slightly modified at the same time? Or maybe I have a bunch of different dynamics I want to explore, and so therefore we have a lot of equations. And in that case, you can actually just essentially run all of your equations at the same time on a GPU. There's a lot of details to this to make it work properly. But so the other case that we will not be talking about today is sometimes you're solving like a big PDE. If you're solving a giant PDE, you can make your linear operations be on the GPU, and then it's easy. You don't need anything special from the SciML land for that, other than linear solve and nonlinear solve and all the other special things we do for that. But you don't need something special for the GPU or for the differential equation side. But if you have many ones, you do actually need, it turns out, some specialized things, because the naive way of parallelizing to a GPU doesn't work especially well, which we'll see. So yeah, the naive way is array-based data parallelism. So that's where you just make your U not be a Q array, and you make your P a Q array, and your T all of your problems a Q array, and then you solve all your problems like that, and then all of your time stepping still on the CPU. And as we'll see, this has some significant overheads. But we're in Julia, and we can do some fancy things instead of that. And this is where we get into custom kernel generation. So with custom kernels, what we're going to do is we're going to generate the method for doing all of the ODE solver on the GPU, and this will dramatically lower the overhead, as we'll see later. But first, there's a number of different packages outside of the Julia land for doing differential equations with GPUs. There's MPGOS, which is C++ and explicit solvers only. There's Diffrax and PyTorch, which are both Python-based tools. The big downside of both of these generally is that they mostly only support the array-based methods, because they're coming from a deep learning-y side of things where you're doing big matrix multiplies, and therefore you don't need some of the fancier stuff. And then there's Janelle Soda, which is a GPU version of the C or Fortran, I forget which, I think C, LSODA solver, which is a stiff solver. And yeah, so given that all of those libraries exist, why do we need to write diffieq GPU ourselves, and why was previous software not perfect? So we have our f of upt, and you generally, like, making your right-hand side run on the GPU is not trivial. You need you need to be in a relatively restricted subset. If any of you have worked with GPUs before, you'll know about the scalar indexing errors that you can sometimes get when you're trying to run things. But to write to make it easy to write high performance GPU code for this sort of case, you basically need to use something like SPMD. So many data single program. But yeah, so the traditional approaches generally don't get the performance you want. And so Ensemble GPU Array is the DiffyQ GPU version of the previous approaches, basically. So you just take a big array of things and you solve it on the GPU, and then you come back to the CPU for your time stepping. But the main innovation of DiffyQ GPU is Ensemble GPU kernel, which is where you do the kernel generation custom. So yeah, this is just going through what it looks like. So rather than having your single U and P, you just put them into a big matrix. And then, yeah, as you can see, the solver ends up looking very similar to what it would be regularly. So you start here, and then your function evaluations and Jacobians are done on the GPU. Your factorizations are done on the GPU. But then you do your step synchronization on the CPU. And then the problem is that this can end up being a bottleneck, or this orange here can all be a bottleneck because that all ends up on the CPU. And launching GPU kernels takes a couple microseconds, and getting data back also takes a couple microseconds, so that can be fairly slow. And yeah, GPUs have the best success when you're doing operations that scale with O of n cubed, or n squared is also pretty decent, but because there the computation is the dominant cost as opposed to data movement, and GPUs are essentially what you get if you take a computer and you throw out most of the complexity that makes data movement and lookup fast, and just stick as much computation on them as possible. So if you have highly computation bottlenecked code, GPUs are great. But the ODE case, you're largely dealing with O of n code, or O of n algorithms. So the data is about the same size as the computation, which makes the GPUs generally be pretty memory bandwidth or bottlenecked. And then the other problem is that because you have synchronization at time stepping, if you have different problems that take a different amount of time, you run into the issue where the longest running one will bottleneck all of the others that finish first. This won't be a problem for some systems, it will be a problem for others. It depends largely on how deterministic your ODEs that you're solving are in terms of how long they take. And so the new approach is that we create a kernel that has the Runge-Kutta steps in it. And this approach means that you only launch a single kernel for the entire solve pipeline of all of the problems on the GPU. And this is completely static. And each thread is giving you a separate ODE. Each GPU kernel is doing a separate ODE. And this means that you get a much better scaling in some cases because you aren't bottlenecked on all of the solvers, all of the time steps having to go back and forth between the GPU and CPU. And so the solver support so far, and apologies if this is outdated, Chris Rokakis in the back will tell me, hopefully, if it is outdated, but we support Seat 5, Vern 7, Vern 9 for non-stiff solvers, which are generally the best in terms of medium to high accuracy. So rel-tol abs-tol of like 1e-6 to 1e-9 or 10 or so. And then for stiff ODEs, we have the Rosenbrock W methods, Rosenbrock 2.3, Rodas 4, Rodas 5p. Rosenbrock 2.3 is the best for ODEs with loose tolerances, so 1e-3 or so. Rodas 5p is generally my favorite ODE solver. It is really good in a lot of cases. DAEs in mass matrix form, ODEs with relatively high tolerances. And then we also have 2 SDE solvers. I do not know much about SDEs, but we support them on the GPU and in the kernel mode. And then there's also the Caverno solvers, and I don't know what they do. I've not used them. And so yeah, as you can see here, with the Ensemble GPU kernel approach, we get there's no synchronization loop. So yeah, you don't have to go back to the GPU or back to the CPU every time step, and this is why it will be much faster. Because yeah, you generate. So yeah, the way that these work is you start with your symbolic representation, because symbolics is a very good way of optimizing your problem. So we can do this from Catalyst, Modeling Toolkit. There's another bunch of others. So I don't know if we've ever tried Ferrite, but presumably Ferrite might also work here. And then from there, we generate the ODE problem. And because we have symbolic frameworks at the top of this pipeline, we can make sure that we only generate GPU compatible code. And then when you call the solve of the problem with a GPU, we will generate a kernel, go through kernel abstractions, which does the Julia compiler with a bunch of specialized things to make it not generate CPU code, but instead generate GPU code. And then that produces optimized LLVM-IR in the same way that a Julia compiler does, because LLVM can also compile for GPUs as well as CPUs. And then that gives you a GPU native device code. So unlike a lot of other GPU frameworks, we don't generate C++ or C. We actually go straight to GPU assembly, which can be a significant optimization benefit. And then also for AMD and Apple, the process is fairly similar, but it gets a little bit different because of some technical details to do with what the GPU stack looks like for those pipelines currently. And so now there's a live demo, and I wasn't sure if this was going to work because I'd heard rumors of SSH being bad, but we seem to have it working. So let's see. Where did that go? Okay, there we are. Where? Okay, cool. So, yes, good call, thank you. How's this? Oh, wait, here we go. So yeah, we can load our packages. Eventually. Time to first plot's not too bad on this. And so here we have just a simple Lorentz problem. It's the classic demonstrator. It's a chaotic system. It's one of the simplest chaotic systems that exists. And so we are going to make a static vector for our initial condition, and then we're solving this on a 10-unit time span. We have our parameters, which are just the traditional Lorentz parameters, and then we can define our problem. This should all be fairly standard to any of you who've used ordinary differential equations before. So where this starts to get a little different from what you might have seen is we're going to define a prob func and then a Monte Carlo problem. And so, wait, first, why is this here? And what? Oh, because I never defined my prob. Yeah, what? Okay. Live coding is hard. And then, yeah, so this is using okay. Oh yeah, I know what happened here. There we go. So this is using ensemble problems, which is an interface in ordinary diffeq to let you solve many problems where you give it a prob func that tells you how to generate new problems. So it lets you very easily make very customized ensembles with lots of different parameters. And so now this system, so if we run lscpu, you can see that we're on a Zen 7 Zen 4 CPU, so AMD EPYC 9000 series, 64 cores, hyperthreading off. And if we do NVIDIA SMI, you'll see that we have a Tesla V100, so pretty high-end CPU, pretty high-end GPU, and we can now show. Why does it do that? I think I might need to escape from this presentation. That might make things work better. Yeah, here we are. So we can run the problem on CPU with ensemble threads. So this is running it in a multi-threaded mode. There's also ensemble distributed for multi-node computation. So this is just our CPU baseline. Apologies for the time, it is compiling. But yeah, as you can see, this takes 14.5 milliseconds, which for solving 10,000 trajectories, that's pretty good. And then if we just run it with a GPU, and this is ensemble GPU array, so this is the one that we expect to be higher overhead. I probably should have started running that before I was talking. But this is also going to take a while to compile. And what we'll see afterwards is that instead of being 14 milliseconds, it will be something closer to 150 milliseconds. So here, like, GPUs are supposed to be fast. What's happening? Also, why is it taking so long to compile? But yeah, as you can see, this was 150 milliseconds. So we used a fancy GPU that we spent $10,000 on, and we're 10 times slower. What's going on here? And the answer is, especially for this example with Lorentz, because it's a chaotic system, you run into the problem where it does get very bottlenecked because all the time steps are trying to communicate with each other, and it has to take a lot of time steps, and so you end up with a lot of overhead. But so instead, if we do the GPU seat5, which is the kernel method, you can see that we're 8.5 milliseconds, and that's twice as fast as the CPU. And so that's a pretty reasonable speed up. I forget. Yeah, so this is float 32, so we have an expensive CPU, we have a expensive but not the newest GPU. This is a 4-year-old GPU, I think. So if we had an A100 in here, it would probably be 4 or 5 times faster. But yeah, even just with a expensive but not top-of-the-line GPU, we're getting better performance than one of the best CPUs that you can get. And so now, exiting this, I'll bring it back in case we have questions about this later. Cool. And then going back to the presentation. Yeah. This, by the way, was me putting all the code here because I did not trust that SSH was going to work because I'd heard bad rumors about it. But we actually have a live demo. And so as you can see in these benchmarks, we're faster than CPUs for most tolerances with the kernels. And this is a work precision diagram. If you haven't seen one before, the x-axis, this isn't a work precision diagram. The x-axis is number of trajectories, y-axis is time. So if you have enough trajectories, so towards the right, you can see that ensemble GPU kernel is a lot faster than ensemble GPU array always, and with more than about 1,000 trajectories, it can be noticeably faster than CPU. And so we are also not advancing slides. And yeah, so benchmarking versus the other GPU solvers from the other packages we were mentioning before, you can see that there's a 100x speed up over tools like PyTorch and Jax. And this is because they are using more of the ensemble GPU method, which has inherently higher algorithmic complexity and overhead. Yeah, so all of the array-based parallelism methods are slow, all the kernel-based methods are fast. And so as you can see also, I can't demo this because this is a Dell rather than a MacBook, but this runs on Metal, so if you have a MacBook, you can get DiffyQ GPU running on that. If you have an AMD GPU, you can run on that. If you have an Intel GPU, Y, but you can run on that also. And you get roughly the performance that you'd expect based on the comparable flops. yeah, and these are just the GPUs that those benchmarks were on. And yeah, ensemble systems and SciML are in general ready for multi-GPU and multi-paradigm systems and HPC. And yeah, as a bonus, if you do some fancy stuff, you can get this running on WebAssembly. If you try doing things that are too complex, it will probably break, though. And I think that is ready for questions, pretty much. And then also after a couple questions, I'm going to show a custom slide that Chris told me I have to show you guys with like 2-hour warning. So yeah.
Okay, so is there any questions? And I'm going to be moving around the mic for you guys.
Thanks, it was a very impressive talk. Have a question whether this kernel dispatch would also work for stochastic differential equations. I assume here it was only parallelization over the initial conditions and the parameters.
Yes, it can. We have 2 SDE solvers implemented, and it is possible to implement more of them. And I do not believe we've done so yet.
Yeah, and so if you use the kernel-based SD solver, so there's the Euler-Maruyama method, but then there's also a method that is second weak order, because if you want to do ensembles, you probably want weak order, right? So there's a second weak order method on there as well. And if your prob func is just run the same function all over and over, then it will basically parallelize that ensemble where it's taking different Brownian motions for the solves. You can also mix, randomness in the parameters and randomness in the Brownian motion and randomness in the initial condition. But I mean, yeah, the case where you just say one set of initial conditions, one set of parameters, and I want to check the property of the stochastic differential equation, you just directly use the kernel GPU method where you just say prob func equals, just use the same problem every single time, and it will give you that Monte Carlo solution, right? And you'll get some pretty nice speed ups with that over the threading methods. Yeah.
Not really a question, but a bit of cheek from me. All Raven problems are dominated by data movement between the CPU and GPU. For AMD MI300A, the CPU cores share 128 gigs of HBM with the GPU. And people have seen huge speed ups in, for instance, the OpenFOAM code. I don't know if you've had a chance to try them. Probably be very interesting to try that. And to be honest, then NVIDIA Grace Hopper does something very similar.
Yeah. I have not had the chance to experiment much with those, but they are interesting possibilities for generation. Give it to Chris.
Yeah. Well, I think that the main answer just is by making the number of data movements and synchronizations essentially 0, because you just run the entire solve on the GPU. That's good no matter what architecture you're on, right?
Yeah.
So yeah, the AMD GPUs, they tend to have like a lower overhead because of synchronization, but it still dominates until you have enough trajectories, right? In fact, if you go back to the plots, you can actually kind of see what happens to these plots. So if you look at these, right, they're almost flat for a while, and then they have that kink in there. That's basically the spot where you've actually filled the GPU up enough, and so that way, until then, the entire GPU run is the same amount of computation. You just haven't filled the GPU up, right? And so for a lot of cases where people are actually using, I want to do 10,000 solves on a GPU, we're actually not even filling the GPU yet. So trying to make sure like there's no data movements at all or anything is actually really essential, because we're just like, we need the biggest GPU the kernel call that we can, because you don't really have that much computation until, if you have 1 million ODE solves that you're putting onto there, yeah, you're filling the GPU. But a lot of people's cases are like ensembles of 10,000 things, and we have to really make sure that we use a GPU well in order for that to matter.
And there's also probably some work in the future on better ODE solver methods for GPUs that use more stages to get you extra parallelism. Oops.
Okay. Another question here.
Yeah, I was just curious if this type of parallelism can handle event callbacks, or if that would kind of kill the performance.
Chris is giving a thumbs up, which is surprising to me. I would have thought it wouldn't work.
Open up the paper. We have examples of continuous events and discrete events in there. Yeah.
Oh,
So
cool.
the GPU is able to. I mean, you need to make sure you're very careful with how you write that code, because you have to make sure that it's completely type stable and everything, so that way we can generate a static kernel for it. But yeah, I mean, things like bouncing ball and stuff. Those are examples that we use to show that the kernel generator is compatible with the event handling system.
Question back here.
One question regarding the array-based methods. With recent CUDA releases, NVIDIA has introduced kind of these graph-based kernel launches, right? Which which don't require your CPU to actually launch the kernel, but instead you can have the controllers on the GPU launch the kernels for you, with much lower kernel launch overhead. Is this something that would make sense to use here, or is it?
It probably would. It probably would make sense, but it still won't be as good as just doing it all in a single kernel. So it's one where if we hadn't gone through the work of inventing this, yes, it would be a great thing to use. But we have the good thing. Just use the good thing.
Can you train neural ODEs with this?
Yeah.
Easy question.
Chris wants to give a more than one word answer, but the
Well,
answer is yes.
so go to the other paper that we just showed. So the next thing is okay, we have ODE solvers that we put on the GPU, but could you also embed nonlinear optimization on the GPU as well if you can do a kernel method? The
Yes.
answer is yes. Well, could you then do a global optimization where you put a GPU, where you build a kernel that has an ODE solve and a nonlinear optimization per GPU core, and then do multi-start optimization from different points in trajectory space, and then you just take whatever the global optimization solution is? The answer is yes. And could you do that with a neural network inside of an ODE, inside of the optimization, all on per GPU core? The answer is yes, and this paper is the example of it. And so you go check out the paper there, and then there is a library, psogpu.jl, or it's gpupso.jl. I forget which way we did it around. So basically all of these tools that we have for GPU kernel generation, we've extended it to the optimization tools. It's not all released now, but all the packages are out there for you to use. And the reason why it's not all released yet is because we're formalizing what simple optimization.jl will look like. Again, if you saw the state of SciML talk, the next thing that we're doing is a lot of making sure optimization.jl is as mature as these other tools, and making sure that we do the right testing on all the optimization tools, so that way they don't break on GPU, is part of this maturization of optimization.
I feel like yes was the short enough version of that answer.
Okay, we have time for one more question, and if the next speaker wants to, you can start getting set up. Or if the next speaker needs to find his partner, he can come on up. One more question?
Just also another question on the behavior of this ensemble problem if for certain trajectories it fails to converge, like it would be fully...
So the way that this the interface generally works is that with an ensemble problem, even if the whole thing doesn't converge, you'll still get answers for the parts that do converge. I'm not sure with the ensemble GPU array whether that will have a short-circuiting behavior, but I don't think it does. It doesn't. Chris is shaking his head, so no. Yeah, you get answers for the parts that we have answers for, and you get failures with ret codes for the ones that don't.